Hello.
Yes, it's clear.
Okay, so let's start. For today, we will study the lesson number 6. It will be about software and hardware for deep learning. The outline for the class consists of 3 parts. One is about hardware for deep learning. We will discuss about CPU and CPU unit, right? And then we discuss about some popular deep learning framework, and then about the mechanism of accelerator and compression tool. Okay, so let's get started with the first part for today. Introduction to hardware for deep learning. Here we discuss about the CPU and GPU. So what you see in the slide is a not so common computer, right? Do you see the uncommon thing in this computer? What do you see in this computer?
I think there are two GPU.
2 CPU, yes. So for the normal computer, you might have only one CPU, right? And for the common computer, you even don't have a dedicated CPU card. You have the CPU chip that was integrated into in the main board, right? And in this one, you have 2 dedicated CPU, and it's a GeForce GTX, and it's quite a good one and a little expensive, right? Okay, um, here we have the comparison between the CPU and GPU. CPU compute processing unit, and GPU graphic processing unit, right? And the differences between CPU and GPU can be in the following characteristic. For example, in the first characteristic about the number of core, the CPU usually have a very less number of core in comparison to GPU. For example, the CPU Intel Core i7 have only 4 core, and you may have up to 8 thread with hyper-threading virtual core, right? And for the GPU, the one we have in here is a RTX 2080 Ti Titan, right? And this one have like more than 3,000 core. So talking about the number of core, the GPU have a much more core than CPU, right? First, discussing about the clock speed. The speed of the CPU, right? Computation. The speed for the CPU is about 4.2 GHz, and for the GPU, it's smaller, 1.6 GHz, right? That's the second difference is. And now about the memory side. For the CPU, it's have a register, it have cache, and it use dedicated external memory unit. Is a random access memory within the computer, RAM, right? And for the GPU, you have integrated memory unit within the GPU. In the case of the RTX 2080 Ti, you have like here 11 gigabyte, right? And for the price, the CPU here is less expensive than the GPU, right? For the speed, if you multiply with the number of core, then this is the speed of the CPU, about 540 gigaflops, floating point 30 bit, 32 bit. And for the GPU, you have much more number of flops. It's about, in this case, 13.4 teraflop, right? So it's much more in comparison with the speed of a CPU, right? So we may conclude that the CPU have fewer core, but each core is much faster and much more capable, right? The number of operation that the CPU can execute is much more than the number of computation. The number of operation, right? It much more. It's more powerful. It's more rich. It's more capable than the CPU. But due to the smaller number of core, it is great at the second tier task, right? Because if you have a 4 core, you can do 8 threads in parallel, but it's not significant as compared to the CPU. So for the CPU, you have more core, right? Much more core, more than 3,000 in this case, but each core is much slower and simpler. The number of operations can be executed by the CPU is very limited in comparison to the operation can be executed by the CPU. And due to the bigger number of core, the CPU can do great for parallel tasks, because you can assume that all the core can do everything in parallel, and they can access different data and do the computation independently, right? Okay, so for example, in the case of matrix multiplication, you have the matrix number 1 and matrix number 2 here. It is A, B, and B, C. And when you do the matrix multiplication, actually you will do multiplication of 1 row in the matrix 1 and 1 column in the matrix 2, and this will be you sum them together, and then you have the value for this element. And then again, when you multiply this one to the second column of the second matrix, you have the new value for the cell in here. So you see the computation for every cell in this result matrix can be calculated independently, and they can be calculated in parallel, right? So this kind of matrix multiplication will be more efficient with CPU than in CPU, right? So I hope that was clear about the advantages of CPU, right? About parallel processing. Here is another graph saying about the cost for computation per 1 USD, right? If it's expensive to do computation or not. So here you see, the blue dot here is for the CPU, and this is for the orange dot here is for the GPU. For example, taking the taking this time step here around 2016, and in that at that time, the cost for the number of gigaflop in the case of CPU is about close to 2 gigaflop per 1 USD, right? If you use CPU to do the computation, and it costs you like it's got you 1 USD for 2 gigaflop. But in the case of CPU, for $1, right, you can have 16 gigaflop, right? So the difference is like 8 times, 10 times, right? Okay, and you see in the case of the CPU, you see the increase in the gigaflop per USD, but in the case of CPU, the increment is so slow, and it's like flat, right? Because it's quite hard for the CPU to scale to a bigger number of core, but for GPU, because the operation that core can be executed is very limited, so they can somehow easy to scale that, dumb core to many, right? And it's less expensive. Okay. Okay, so now we have the graphs showing the comparison between the GPU and CPU in practice when you do the narrow, when you do the neural network processing, right? And here we have comparison for the VGG 16 layer architecture. This is VGG 19, this is RedNet 18 layer, this is RedNet 50, and this is RedNet 200. And we compare the time to do 16 forward and backward step, right? And in the case of using the CPU, it takes quite a long time. And in the case of using the GPU, when you don't use the QDNN, this is a specific library provided by NVIDIA for doing the deep neural network processing. So if you don't use that specific library, you still have the speed up of 66 times, right, over the CPU setting, right? And in the case of using the GPU with the QDNN library, and you even have a bigger speed up, about 76 times, right? You see the difference between the with and without the QDNN library. Okay, so that was the reason now that if you want to train a very big neural network architecture, you should have GPU. Otherwise, it will take you a long time to do everything with CPU, right? You see, if you train something in CPU, take you 1 day, and for CPU, it might take you 66 days, about 2 months. Okay, do we have time to wait for 2 months for that thing? Okay, this is that 16 forward and backward part. You see. Okay, so this is a comparison with between again CPU, GPU, and GPU with QDNN library. So you see the QDNN is much faster than unoptimized CUDA, right? It is just the CPU using with a special library designed optimally for neural network computation. You see the boot up is about 3 times, right? 3 times, okay, around 3 times for every different network architecture, right? Okay, so you have GPU here. You have a GPU for today. You might have a RTX 3080 Ti, right? And that's something you can buy for the personal computer. If you have more money, you can buy the DGX special CPU server, but it would be really costly. Okay, so besides CPU and CPU, you have special tensor processing unit. Its name is TPU. So you have TPU provided by NVIDIA, and you also have the TPU provided by Google, right? And if you use Google Cloud, you can have the access to TPU, right? For the number of core, we have no information about the TPU of Google Cloud, but for the NVIDIA, you have much more number of core, right? It have more than 5,000 CUDA core and 684 tensor core. Clock speed is a bit smaller. You have more RAM. It's more expensive, but in this case, you have much more capability. So if you double the price, for example, you have much more teraflop for floating point computation of the float 16 bit, right? It's 112 teraflop, right? It is the advantages of using the Tensor Core, right? And in the case of GPU, you have you have to pay per hour. It's a little bit more expensive, but the number of teraflop here is about around close to 200 teraflop, right? We have much more RAM. Okay. Okay, so let's continue. Now we have the now we want to compare the gigaflop per USD of different hardware for deep learning. Here we have CPU, TPU, and GPU. You see, okay, the CPU is somewhere here. Okay, this graph is a little obsoleted 5 years ago, but again, it's still helpful for us. In the case we have the Titan V, it have a Tensor Core, it's just a CPU, and you see the cost for, I mean, if you have $1, I mean, you can do much more gigaflop. In the case of here, in here, you can do 40 gigaflop for $1, right? Okay. So here, the nice thing about the NVIDIA DGX server, right? So for this server, you have you can have it is special server computer. You have 16 CPU in total, right? 16 CPU, right? It's a lot, right? A normal computer have 1 or 2 CPU, but this one have a 16 CPU. And each CPU is the NVIDIA Tesla V132 gigabyte. Okay, even this one alone is so powerful compared to the 3080 Ti we have nowadays. Right, we can buy that one for the personal computer, but this one is a server one, and you see, one Tesla V100 have a 32 gigabyte memory. You have the NVSwitch that can provide high-speed interconnection between the, I mean, between the different, I mean, between different this CPU, sorry, different server, right? Then you have what? You have infinite band to connect, I mean, the internet network connection, and the NVSwitch is for the CPU connection. And then, okay, about 1.5 RAM, okay, and 1.5 terabyte RAM lost, right? Okay, and you have a 30 terabyte SSD. So it's so expensive, this one. It's cost you around 200,000 USD at the website. If you want to bring this one back to Vietnam, I think you have to double the price somehow. Okay, so besides that expensive hardware, we can have the hardware to do deep learning in device. Here we discussed about the NVIDIA edge computing. For example, you have the Ryzen Nano, you have Ryzen TX2, and this is a Ryzen series. This is small device that can be used with embedded system. For example, you might think about deploying a small system that control the user coming and coming out of the building, right? And you capture the human face and detect if this person was is a existing employee or not, right? And in that case, you might use the Zetson Nano or Zetson TX2 series and do everything, including the inference of the model within the device, right? Okay, so for Google, they have Google Coder, something similar to Zetson here, but I think it's less popular than the NVIDIA Zetson series. This is a little, accessible, right, for everybody. $100 for this one. This is only $200. Yes. Okay. So we have a device from AIM company. Here we have AIM ML processor, and we have AIM Mali series, right? So in this special, processing unit, you have, can you see what in here? You see last number of core, right? You have that number of core to do parallel processing, right? Okay, what's else? Okay, so this is a broader ecosystem of AIM and Pure. Right? They have brought the range of ML optimized processing solution. For example, if you do, if you do inference with small model, you can use the Cortex-M series. If you need to do a bigger job, it would be the Cortex-M 55 series. If you need to do, more harder jobs, then you can do this Cortex-M and Nano series, and then you can do the Cortex. You can use the Cortex-A and Nano N series to do things like object classification and real-time recognition, right? Okay, so that was about the hardware using for deep learning, and talking about the hardware we might have. We should have the driver associated with the hardware, right? For example, if we use NVIDIA GPU, then we have the CUDA library that will allow you to write C-line code that run directly on the CPU, right? You have optimized APIs such as the cuBLAST, cuFFT, and cuDNN. It is quite popular that is used by most of the popular deep learning framework nowadays. You have OpenCL. This one is similar to CUDA, but run on anything, not only the NVIDIA, but other GPU device. And usually it's slower on NVIDIA hardware. Of course, because it is designed by NVIDIA and provide for NVIDIA device only, right? You have a HIP SIP, and it is a new project, open source project that automatically convert CUDA code to something that can run on AMD CPU, right? If you need to do that specific work, you might try the HIP. And I see that most people nowadays using CUDA. So, this is popular, easy to access. Okay, so talking about training a deep neural network, what you can discuss here is the location of the model and the location of the data, right? When you do the training and inference, the model is within the GPU device, right? And the data is somewhere, in the hard driver, right? Or it could be in RAM, right? So if you do the inference or training, you need to copy the data somewhere from here to here, and then copy back the data from here to there, right? So if you aren't careful, then the training can be bottleneck on reading data and transferring the data to GPU, right? And this is a problem that you might observe quite often in practice, right? So the solution for this is to somehow, for example, read all the data in RAM, or you can use SSD instead of SSD, because the speed of SSD is much faster than SSD, right? Or you can use multi-CPU thread to fit the data, and this is something that you do this often, because the library, the deep learning libraries such as the TensorFlow or PyTorch, they can allow you to use this mechanism easily. Define the number of worker thread used for fetching the data, right? Okay, so that was about the hardware for deep learning. Do I have any question for this part? No question. Okay, then we might stop for 5 minutes to break, and then we will continue. Okay, so let's continue. Do you still hear me? Hello.
Yeah, it's clear.
Okay, so I got one question from Huy Hoàng. Can you explain more about edge computing? Okay, edge computing refer to the way that we doing the computation within the device. This is something I mean in the opposite direction of cloud computing. In cloud computing, you have everything, the server side running on the cloud computer, right? You have for example, you have the mobile phone, you have the computer that access the application in the cloud. So everything you have within the device, that's the interface, right? Every processing is done within the cloud. For example, you can, for example, you can do you can do you use a device just to collect the data, right? And the processing will be done in the cloud. That is cloud computing, right? Another example is, for example, if you want to deploy the face recognition in the cloud setting, you have that the camera of the device used just to capture the image, the video, right? And then when you capture the video, you have to send the video to the cloud server, and the cloud server will do the inference, and then it will give you the output such as this is a real face or this is not a real face, right? So in that cloud setting, the device is used just only for collect the data or to produce the data, right? And every processing will be done within the cloud server. In edge computing, what you want to do is to have the computation running within the device. For example, that edge computing could be a small device that have the camera doing the same work as to detect the real user or it is not the real user. But in edge computing setting, you have the collection of the data and then the processing of the data within the device. So in that case, you don't have to send the data over the network to the cloud and then receive the answer from the cloud. You do everything within the device. So in that case, that's why you need need the GPU device. For example, you need the NVIDIA edge computing here. You need to have the Desktop Nano, that small device within the small hardware, and then that can do the neural network inference within the device. Is that clear? What is better, cloud computing or X1? I think it will depend on the situation, and I think that in the future, the edge computing and the cloud computing, they will work together. Some processing tasks must be done in the cloud, and some simpler tasks can be done in the edge device. Right? So there's no clear winner in this. I don't see one approach maybe. More advantages than the other approach. They will. Core. Cooperation. Any question? If you have no question, then we can continue. In which solution we use cloud computing? If you have cloud setting, then it could be easy for you to control the environment, right? And you may do the computation with the, more cheaper, right? Because you can pull all of the processing to be done at the server, and you manipulate the server in an efficient way. And in the edge setting, you need to have a lot of, you need to, for example, you need to deploy a lot of device, and each device have a specific, NVIDIA edge computing unit for this one, and this will be expensive, right? That's a nano alone cost you 100 USD, right? And in the case if you just have the device that collect the data, then the camera is so cheap, right? You can just use the camera with the Raspberry, and this costs you less than 30 USD, right? Any question? No other question? Okay, then I think that we will continue, right? Okay, so now we discuss about the deep learning framework. There are many deep learning framework nowadays that you can use. For example, Caffe2, Toast, PyTorch, and TensorFlow. And okay, so you see the Caffe was originated at UC Berkeley, and then the Facebook take over, and then they made the improvement and release the Caffe2. For the Toast, it was originated at New York University, and then the Facebook engineer make a nicer version, Python version. Theano was developed at the University of Montreal, and is then have a nicer version. Is provided by the Google TensorFlow. You have the Pater from the Baidu company. Trainer is this one from I don't know. The AmbigueNet is sponsored by Amazon, and the CNTK is sponsored by Microsoft. And you also have another deep learning library from Google, right? So I see the most two popular deep learning framework nowadays is this one, the PyTorch and TensorFlow. So AmbigueNet is also popular. Yes, so now we discuss about the computational graph in neural network. Right, for the neural network, what you have in terms of implementation is the computational graph. You have the input X, and you have this W is the weight of the network, right? And then you have that net input, the multiplication of W and X, and then you what you do here is to compare the output of the model with the routers, and that comparison is doing the computation of the cost, right? And then what you have here, and this is okay, this is just a computation of the score, and then you combine it with I'm not sure, but this is to computation to compute the loss. I mean, after you have a specific training pair, right? And this is a bigger computation graph. In this case, you see the data flow. The data is like the water and flow through the Pi, and the Pi is just the collection of different units in the network, right? For example, in the input here, it first go through the reshape processing, and then do the multiplication with the weight, and then you add the bias, right? And then you do the activation, the value unit, and then you do another math multiplication with the weight of the logic layer, and then another addition with the bias, and then you do submax, and then you do the clock entropy to calculate the loss, right? Okay, and then you do the gradient, and when you do the gradient backpropagation, you update the weight and you update the bias, and you update another weight for, and then the logic layer and another bias, right? So this is an illustration for the computational graph with a specific neuron. It's not big, but it have I mean the complete visualization of the forward pass and then the back propagation pass, right? So you can define the computational graph using the NumPy library. For example, you will define here, you import the library, you initialize the seed for the random function, you define the dimension, and then you initialize the x, you initialize y, you initialize dash, and then this is a computation. You have a equal to x multiplied with y, b equal to a plus z, and then c, and d are the definition of specific node in the graph a, b, and c. These are the definition for the inputs x, y, z, and these are the computation node, right? And you can use NumPy to actually doing the gradient computation. For example, you can manually set the gradient C and then compute the gradient B, gradient A, gradient Z, and gradient X and gradient Y. So the advantages of this approach of using the NumPy is to have clear, clean API, easy to write numeric code, and it is clear for everybody that know how to use the NumPy library, right? But the disadvantages of this one is to have to compute the gradient manually, right? We have to write the gradient computation, and another drawback of this approach is this can run on CPU. Every computation we are doing here is running with the CPU, right? So if we don't use NumPy, then we have much more a nicer way to use for represent the computational graph is to use the NumPy, to use the PyTorch library. So for the PyTorch, it's again that's one library in Python language. You can import as a normal library. Here you define the same dimension, you define x, y, dash, and then you again you define the same for the node A, B, and C, right? So everything is much more similar to NumPy, but you have this beauty characteristic functionality. The PyTorch can do auto gradient, right? So instead of writing this gradient computation manually by yourself, if you do something wrong in here, then that will go wrong, right? if you do the PyTorch, if you want to backpropagate the gradient to that x, then you can on the definition of x, you can say that okay, for x you want to initialize x with this special dimension, and you have this special property, the method parameter saying that okay, for x you require the grad, you require gradient equal to 2, mean that you want to do the backward gradient to this param. Okay, and then you can just say c dot backward, and then the gradient will go through from c to x, right? And then you can print the x dot gradient, right? So in this case, you don't need to do the gradient manually, so you can avoid the mistake that you might have with the manual approach like this one. So everything will be done in a correct way with the PyTorch library. Okay, so the point of deep learning framework is to be able to have a quick way to develop and test new idea, right? You will have to write everything from scratch, like using the NumPy library in here. It will be very slow and very complicated, right? Not so many people will have time to write everything in a manual way like this one, right? So the idea of the framework is to help you to develop and test new idea quickly, and it will allow you to do automatical computation of gradient, right? So you don't have to care about what are the gradient computation for specific node, right? And another advantages of using deep learning framework is to have fast access to GPU. So if you write the program with the deep learning framework, then it can run efficiently on GPU, right? And you have the access to the cuDNN, cuBLAST, and OpenCL, the optimal driver for GPU hardware, right? So the other thing that you have if you use a framework, right? And I hope that most of you will use the framework for the test, right? You don't need to reinvent the wheel for the normal work, right? If you do something more advanced, more innovation, then you may, for example, extend the framework. It will be really rare to develop a new framework or develop everything from the scratch. Even if you do the deep learning for edge device, nowadays you still have the access to specific library that will help you to run deep learning model within the edge device. Okay, so now we discussed deeper a little bit with the PyTorch library. So first we discussed about the tensor in PyTorch. So a tensor is like a NumPy array, but it can run on GPU. Okay, this is nice, right? And the data model and API are too much the same. Okay, very nice. Here's an example of training a two-layer neural network using the PyTorch tensor. You import torch, and then you have special variable saying that you want to use the CPU device. If you want to train this to be CUDA, then you can just say torch.device, and then inside the parenthese you say CUDA, right? And then you define the dimension. Okay, you initialize the X on the device. Here is on CPU, initialize y w1 w2. Okay, and now this is something similar for doing the backpropagation training. You set the learning rate, you do a loop for this specific step, and then you do the computation for, I mean, this is a hidden layer, this is with the value, and then you compute the prediction of the network, and then you compute the loss. Here you will, this is a square arrow, right? Yeah. Of the vibration and then the labor, right? And then you do the gradient. Oh, in this case you don't use auto gradient setting, but you really do the gradient computation manually. Okay, and then you update the weight W1, W2, right? Okay, so this is a introduction to the tensor. Here you have the X, Y, W1, W2. They are the tensor, so they aligned to NumPy array, but they can run on GPU, right? And if you want to run with the GPU, you can just train the device to be CUDA. Okay. Okay, so now we have an example of auto gradient with PyTorch framework. You create the tensor with the required graph equal to true to enable auto grad. And torch no grad means don't include it in the calculation graph, right? Usually for the weight of the network, you had to set the required weight equal to 2, right? So this is something typically specific to PyTorch. We need to set the gradient to 0 here before starting to do backpropagation. Because the PyTorch will accumulate the gradient on subsequent backward pass, and this is convenient while training RNN, right? If you don't train an RNN, then you don't need to accumulate the gradient. So that's why you need to remember to add the grad 0 here. Okay, so let's see what is different when we have auto grad. Okay, this is required auto grad. Okay, then you will compute the prediction, compute the loss, and then you just say loss backward. You want to backpropagate the arrow signal from the output to every layer in the network. And here we need to compute the loss for loss signal for W1 and W2, right? And then with torch no grad. Okay, in this case you do the update to W1 and W2, and then this is the step where you zero the gradient before the next step. So do I have any question? Okay, so let's continue. In PyTorch, you have the NN package. So in this package, you have the high-level wrapper to work with the neural network, and it makes the programming become easier. For example, here you instead of define the loss this way, and this loss is popular, so you can use that MSE loss in the NN package, and you can say loss equal to talk.nn.functional.msi loss. So remember that this part might be different from the in different version of PyTorch, right? So it might change in the future, or I don't know. So you can check the manual to see the correct location of the specific function that you want to use. And you see here in the NN package, you have the wrapper for definition of specific layer. So here you define a sequential network, and then in that sequential network we have the first layer is linear, and then the value, and then again another linear, right? So when you say sequential, it means you stack everything one after the other one. Okay, so here you say zero graph for every gradient-able parameter in the model. So you don't need to say graph for every weight. If you do the model.zero graph, it means that you zero graph for every gradient-able parameter. Okay, so you can define new module in the NN package. So the module can contain weight and other module. So if you define the layer this way, then the PyTorch will automatically hand auto-grade for new module, right? So in this case, you have the two layer class that inherits from the NN module, and in that case, you need to define the forward function, right? And you have to init the layer, and if we define this way, then the PyTorch will be able to do the auto grade with the layer. For example, here the definition and definition of x and y, and then you define the model, and then you define the optimizer. Here we use the SZD optimizer, right? And then you define the loss. We compute the prediction equal to model, and then the parameter you put the input x, and then remember about the block backward, and then you call the optimizer step. If you all use the optimizer this way, you don't need to update the weight in a manual way, right? Here we have to update the weight manually. Prime equal to prime minus learning rest dot param grad. In this case, we can just say optimizer dot step, and it's the same as doing this here. And then remember to have optimizer dot zero graph. So here's the optimizer. So instead of using SZD, you can use ARAM. So the discussion about different optimizer we already have in the previous class, right? Okay. Anything to discuss about the file? Okay, for PyTorch we have pre-chain model, right? And you can easily access to pre-chain model in a PyTorch repository or anywhere in the internet. Nowadays it could be easy to collect the pre-chain model. So for example, if you use the pre-chain model from PyTorch, you can say import torch vision specific for the vision processing, and you can load a pre-chain AlecNet model, torchvision.model.alecnet, and then you say pre-chain equal to true. This is the 16 redness 101. Okay, so very fast to have the pre-chain model, and then you can fine-tune it with your data, right? Okay, so here is PyTorch Wisdom. It's a tool to help visualize the calculation process. Currently it does not support the visualization of computational graph structure. So you may check if it is updated for the new version. You can use a TensorBoard X in PyTorch. So if you have been working with TensorFlow, then this is a similar interface, right? This is the interface of TensorBoard, and for the PyTorch, you can use TensorFlow X, like wrapper of TensorFlow, TensorBoard for PyTorch. So for this TensorBoard, you can visualize the training process, visualize um, the value of a different rate, different loss, and whatever you want to call it, right? Okay, so okay, so do we need to okay, so let's stop for another 5 minutes and then we will continue. Okay, so let's continue. Are you still there? Okay, so let's continue with PyTorch dynamic computational graph. And okay, so in PyTorch, when you define the computational graph, the graph you have is dynamic, right? Here we have the exam. Import PyTorch, import Torch. Then here we define the W1, W2, and Y, right? And in this case, we have W1 and W2 and Y in the left, right? And then, I mean, when we have the computation for the E prediction, the output of the network, we have the formulation for the weight of the network computation, and the PyTorch will dynamically generate the associated graph for that computation, right? And then in the next line you have the loss definition, and in the execution of the loss, the PyTorch will create the subgraph associated to that computation, and it is something in here, right? And then you do the loss backward, and then the arrow signal will go through the output in the input, right? And for the next iteration, right, when you are somewhere here, I mean the graph, the previous graph will be deleted, right? And it will be rebuilt from scratch, right? In the next step, you recreate the graph, and then you do the backpropagation. So in this case, computation seems a bit inefficient, especially when building the same graph multiple times, right? So we can define the start graph in PyTorch. So in step 1, we build the computational graph. We describe our computation, including the include finding path for the backplot. And in step 2, we reuse the same graph on every iteration. So we don't need to rebuild the graph again. Okay, here is the difference. We build the graph, and in that case, we don't clear the graph for the next iteration, but we can view, right? So that's the idea about the static computational graph. By default, the graph in the PyTorch is dynamic, right? In TensorFlow, do I have question? Okay, so no question. So in TensorFlow, in the TensorFlow P2.0 version, and version lower than, smaller than 0.20, then they have they follow the static computational graph approach. In that approach, we have 2 steps. So in step 1, we build the calculation graph, and in the step 2, we run the calculation graph several times according to the iteration, right? So that was the design, the static computational graph approach of TensorFlow P2.0, right? In TensorFlow 2.0 and newer, we have TensorFlow eager execution mode. It is an imperative programming environment that allows immediate operation to be executed without the need to build a computational graph. So in this case, you have dynamic computational graph. So operation will return specific value instead of building a graph of the calculation and run it later. So this makes it easier to get started with TensorFlow model and easy to debug. Right? So in the case of dynamic computational graph, we don't need to wait for the graph to be built and then do the computation. In this case, we can debug easier. But in the case of static computational graph, you have to place and then do the computation on the graph. And in this case, you may have you in this case you may see fast computation, but it will be harder for you to debug, right? So that's why in TensorFlow 2.0, eager execution mode, so that it will be easier for you to debug the model, right? Okay, here's the difference between the TensorFlow 2.0 and TensorFlow here 0 version. This is the same. So not the same. This is a part for the definition of the input weight and the output. In the eager mode, you can just define, okay, this is tensor x, this is tensor y, this is a variable. Variable is mean weight, right? TF variable W2, and then this is a gradient by propagation part. With gradient TF at TF, and then you calculate the age, the prediction, you compute the loss, and then you do the gradient by propagation. In TensorFlow 1.13, you need to define x, y, and W1 and W2 as a placeholder, right? And then you define the other computation node in the graph for the age, for the e predict, for the diff, and then for the loss. And then you define the the gradient for W1 and W2. And then after the creation of the graph, you start a session, right? And in that session, you use that predefined graph. You assign the value to x, W1, W2, and y, right? In the beginning, you just define the placeholder. You don't have the data at all. For the running, you start assign the value to the placeholder, and then you run the session, and you want to evaluate the loss, the gradient W1 and the gradient W2, and then the input is a value, and then you take the output at the loss, the gradient W1, and then the gradient W2, right? And that was the TensorFlow prior to 2.0 version, right? Yes. So in this case, you see it will be a little bit harder to debug because you only average the value after you define the graph. And in eager mode, when you define x, you assign the value, and then when you can compute something, you got that data, right? Okay, so this is some specific discussion on TensorFlow framework. You can turn NumPy array into TensorFlow tensor, convert to tensor operation, and this is a way to build the dynamic computation graph. you use a gradient TF, right, to record. The computational flow, and use that flow to do the gradient by propagation. And yes, it is say that the operation in the forward step are tracked for later gradient calculation, right? And then use the step dot gradient to calculate the gradient, right? Yes, let's continue, and then we may do a quick demonstration of using the two framework if we have time. Okay, so okay, that to demo the way of using TensorFlow for training the neural network. You have the loop, right? And inside the loop you have the gradient TF, and inside that you calculate the gradient and you update the weight. Okay, W1 assigns the new value, the previous value minus learning rate multiplied with the gradient. Okay, nothing difficult to understand. You can use a predefined optimizer provided within the framework. Here we use a SGD optimizer. You can use Adam optimizer, whatever, right? Yes, so instead of using instead of manually calling the tab dot gradient to calculate the gradient, you can just say optimizer dot apply gradient, right? Okay. We can also use predefined objective function such as the mean square arrow here, right? Anything else? Okay, about the high-level wrapper, the Keras. So in the beginning, Keras was a separate library where you can define big neural network in just a few lines of code, and every layer can be defined by that one single line of code, right? So people use Keras quite often, and then at some point, the developer decided to integrate Keras into the TensorFlow framework. And now, when you have TensorFlow, you can use Keras, right? So it's make Keras make common thing easy to do. So, for example, here you can define the model at a sequential layer, one layer after the other layer, right? And then you add in the model a dense layer, and then you add to the model another dense layer, right? So in this case, you have a model having two layers, right? Two dense layer. So it's a fully connected network of two layers. And then you define the optimizer, okay, the loss, and then you do a loop for the number of iteration. And then inside that gradient TF, you compute the output of the model, you compute the loss, and then you compute the gradient, and you apply the gradient to the chainable weight, right? It's called chainable variable, right? The same thing. Anything else to discuss? Okay, so here we have a more extensive example of using the Keras high-level wrapper. We define the model at the second layer, right? Get output by calling the model. We apply the gradient. Okay, so that was a way that use Keras to define the model, right? But you may use Keras also for handling the training loop. Yeah, we define the model, we define the optimizer, then we compile the loss and the optimizer, right? And then we use a model fit, and in that model fit we provide the data pair, the input, and then the label. We define the number of epoch, we define the batch size, right? And you see, if we use Keras for handling the training loop, you see everything look quite simple, right? It's like using the sklearn library, right? Okay, so in TensorFlow 2.0, we can use a TF function. It's a decoration that compile Python function to static graph for better performance, right? And by saying in static graph, that means that the operation will be compiled, will be available for using in the subsequent step, right? Here we compare the forward pass time of the same model under dynamic graph and static graph mode. Okay, let's say we have the model static, and here we have the model dynamic. Right? In that case, in the static and dynamic, we just compute the output and the loss, right? And you see the difference between the time for the dynamic graph and then the static graph. Is it so different? Is there anything wrong with that? Okay, let me check. Erase the pen. I think there's something not understandable in here. But normally, when you compile Python function to static graph, you will have better performance. And the time to execute static graph must be slower than dynamic graph. I will check the slide again. So let's continue. For the TensorFlow, you also have the access to pre-trained model in TF Keras and TF Slim, and you have TensorBoard to visualize the training process by having by allowing to add log in the code to observe the objective function, the parameter you want, and you can run several TensorBoard and see the result to compare different execution, right? Okay. So for example, here's a comparison between the static and dynamic graph. For example, when you define the graph, it's like this stack, and if we convert that graph to be static, then the framework, the library can fuse the operation together, and it will create an equivalent graph, much more efficient for computation. So for example, here we see the two may be the same, but here you have fuse operation that can be run more efficient, so that you have a good up in terms of performance. Static and dynamic optimization. In the static approach, on the graph view, it can we can serialize it and run it without the code that build the graph. In the dynamic approach, the graph building and execution are intertwined, so always need to keep code around. So For the PyTorch, you got dynamic graph by default. In TensorFlow, the previous version of 2.0, you have a static graph approach, and for the newer version, you have dynamic graph approach. Okay, Cafe with static PyTorch. Okay. Okay. So we may stop for 5 minutes again to break the part, and then we will continue. Any question? Hello. What are pros and cons of PyTorch compared to TensorFlow? So in the past, usually the TensorFlow is somehow more popular than the PyTorch, and the TensorFlow is used in the industry, but the PyTorch was mostly used in research environment. So that was something in the previous years, but nowadays in the recent year, people start using PyTorch quite often, even for the production environment. So I'm not sure, but maybe TensorFlow it's not up to date to the it is because the TensorFlow have less attention from the research community, so that when the researcher they build a new model, they stick with the PyTorch, right? And then the engineer they follow the researcher approach. They see the code in PyTorch, and then they continue working on PyTorch. So maybe that was the main reason why people become, more and more using the PyTorch even in the production environment. So I think that was the main driver for that movement was from the community, right? The community now, the community in the deep learning are driven by the researcher, and the researcher choose PyTorch. So everything move following. Any other question? About the pros and cons. So the TensorFlow was in the past for the production environment, so it's more reliable, more stable than the PyTorch, right? But nowadays things change. In the PyTorch, you have access to up-to-date model, right? In the PyTorch, maybe you had to wait for someone to convert the model from the PyTorch. Any other question? Okay, so let's have 5-minute break, and then we will continue. Okay, so let's continue. Do I have more questions? Okay, so we can continue in to the last part of the lesson for today. Here we discuss the accelerator and compression tool. And okay. Okay, first here's is TensorFlow Lite, and the TensorFlow Lite is a setup tool to optimize TensorFlow model to make model more compact and being able to infer faster on mobile platform. So for example, you can use normal TensorFlow framework to build the model, right? Here, my pen. Okay, you use the normal TensorFlow and then you produce the model that can be run in the computer, right? And then you can use a converter to actually convert that model into the TensorFlow later format. And this format is compact so that you can load the model and run the model in the device in the mobile platform. And when in the mobile platform, you have the TensorFlow Lite interpreter that can interpret the TensorFlow Lite format, and it will allow it to be run with the hardware aggregation interface of the mobile platform. We have TensorFlow RT that's also doing the model compaction and optimization so that it can be run in a different device. And this is a value added by the TensorFlow RT. It have layer and tensor fusion so that it can have a compact representation of the graph, efficient computation on the graph. It have a precision calibration. For example, for the weight, if you use the float 32-bit, and if when you combine with the TensorFlow, Tensor RT, it might decide that you might need, you might not need to have a floating point 32-bit precision. It can, reduce the precision to be that 16-bit, for example. Then you add a smaller model, but no or very little reduction in terms of performance. It can you can have multi-stream execution. You can have dynamic tensor memory and kernel auto tuning, and then you have optimized inference engine, right? For example, the Tensor RT can accept the model from TensorFlow, from MXNet, Caffe2, Python, Theano, and then you can run the model in Tesla P4, P2, Tesla V100, and that's an T2, whatever. This is just an example of running the model in different hardware setting. And you got like speed up in different application. For example, for automatic speed recognition, you have the speed up of 21 times. For NLP, for deep recom, I don't know, text-to-speech, video and image processing. So the speed up is quite big. So if you have NVIDIA device, you must, I suggest that you try Tensor RT to actually compact the model to have better representation, and then it will be, faster to infer. right? Other tools such as Pocket Flow, Tencent, and CNN. So you have a right effective throughput here is, I mean, this is comparison of different model. This is TensorFlow, right? This is CNN, and the best one is Pipe8 here, right? Okay, so you may read all the reference in the CS 231 and whatever in this slide. Any question for the lesson for today? Hello. Any lesson for today? Okay, so if you have no question, then I suggest you check the lab that I sent to you. Which was the lab that I sent to you? The lab number 1 about introduction to the neural network. Did I send to you the lab on convolutional neural network? Hello. Hello. Do you hear me?
Yes, we are here.
Yes.
Okay, so what did I send to you about the lab? Did you get the lab on the convolutional neural network? Okay, the last one is INN. Okay, right. So I suggest that you take time, the remaining time of the class, to practice on the lab. So I give you like 15 minutes, and then I will be back to check your progress. Is that clear? I mean the lab for, I mean, if you already did the lab for the first lesson, then you can do the lab for the subsequent lesson about the CNN, about the INN. Okay, so my suggest that you start to you work with the CNN lab, okay? So that everybody will work on the same thing. Is that clear?
Yes, I think it's okay.
Okay. Hello. Okay, so I think that we can check the attendance of the class for a couple of minutes. Okay, so we have question about the cost project. Let's do it later on. Đỗ Quốc An. Đỗ Quốc An.
I'm here.
Okay. Lê Đức Anh.
I'm here.
Nguyễn Hoàng Anh.
Có.
Nguyễn Minh Châu.
Here.
Phạm Văn Cường.
I'm here.
Tạ Việt Cường.
I'm here.
Nguyễn Hoàng Đăng.
Dạ có.
Hà Vũ Thành Đạt.
Dạ có.
Bùi Anh Đức.
I'm here.
Nguyễn Tuấn Dũng.
I'm here.
Phạm Đình Gia Dũng. Chu Hoàng Dương.
Có.
Lê Trường Giang.
Có.
Đặng Vũ Hoàng Hiệp. Nguyễn Huy Hoàng.
I'm here.
Nguyễn Việt Hoàng.
Có.
Hà Việt Hùng. Nguyễn Duy Hưng.
Có.
Phạm Thành Hưng.
Có.
Lại Quang Huy. Vũ Quốc Huy. Hoàng Văn Khánh. Trần Quốc Khánh.
Có.
Đặng Thanh Lâm. Đặng Thanh Lam.
Có.
Trần Quốc Lập.
Có.
Đặng Nhật Minh.
Có.
Nguyễn Quang Minh. Phùng Hà Nguyên.
Có.
Hoàng Nguyễn Minh Nhật.
Có.
Nguyễn Đức Phú.
Có.
Nguyễn Hoàng Nhật Quang.
Có.
Lê Hải Sơn. Hoàng Thiện Tâm.
Có.
Lê Thành Thắng.
Có.
Phan Đức Thắng.
Có.
Kiều Trọng Thành.
Có.
Phạm Việt Thành.
Có.
Nguyễn Văn Thịnh. Phạm Như Thuấn.
Có.
Nguyễn Văn Toàn.
Có.
Nguyễn Thị Trang. Nguyễn Vũ Thiên Trang.
Có.
Phạm Thanh Trường.
Có.
Phan Mạnh Tuấn.
Có.
Nguyễn Văn Thanh Tùng.
Yes, I have.
Nguyễn Quang Tùng.
Có.
Phùng Quốc Việt.
Có.
Vũ Quốc Việt. Phạm Cát Vũ.
Có.
Okay. So about the cost project, what are the deadline? The deadline for the project, we will have the last, I mean, how to say? in the end of the last of the class, we will have like 2 or 3 2 or 3 weeks for the presentation of the capstone project. Let's check how many class, how many group we have. We have 10 groups, so I suggest that we have to reserve like 3 weeks for the capstone project presentation. Yes. So I see that you guys don't have a link to the Google folder, so you should add soon. For the next week, I think that we can have the first checkpoint of the capstone project, where you have to discuss about the current progress and what you would do in the project, right? For the topic, I already show you different type topic that you may choose for the capstone project. So I don't see you have any question for the project subject. Can you check the project proposition and give us feedback? This is something that we would do in the next week, right? What is our exact expectation on our work? For the expectation, that I have some suggestion in the previous class, such as in the project you should discuss the following tasks, such as data pre-processing, network architecture, hyperparameter tuning, model visualization, and training debugging. And then you can discuss of the on the experience again during the working of the group. So that was the thing. You can choose any topic for natural language processing and computer vision, but I really hope that you don't choose a topic by that picking a paper, seeing that they have the code, they have data, and then you can rerun the code to have the view the trained model. That's something really easy that everybody can do. So I expect from you to do something more elaborate in terms of data pre-processing, hyperparameter tuning, model debugging, and whatever, right? Are 2 groups allowed to choose the same topic? Yes, but I don't think that you are totally the same, right? Any other question? So for the next week, I confirm that for the next week we will have no new lesson, but we will reserve that week for discussing on the topic. You will try to apply 5 different models on the same data set to examine their performance. It's fine, but again, you have to do thing in detail. You cannot say that okay, you have a 5 model and here's the result, right? I really want the discussion, what wrong and what good in which model, right? Any other questions? For the topic, Bitcoin prediction, sentiment, image classification, conditional image generation, object tracking. traffic sign classification. I see that for the topic you are choosing, it was, I mean, they are quite zero, and I cannot say anything about the quality of the topic, right? So I expect that for the network you have more things to say other than that image classification and neural machine translation, right? That was the quite broader topic that it can do anything. So let's try to be more specific on the topic. Okay, so that's enough for today, and thank you, and see you in the next week. Bye bye.